In this video, I'm going to discuss how to calculate and interpret Cohen's d when carrying out the one sample t-test, independent samples t-test, or paired samples t-test using SPSS. Cohen's d is essentially an effect size measure, and the reason why we are concerned about effect size is that oftentimes or generally when you run your statistical analysis, the significance level that you get, namely the p-value, is impacted both by the magnitude of the effect being studied and sample size. And so it becomes rather difficult to just look at a p-value and isolate the effect size from that index, because it is also heavily impacted by sample size. So it can be the case where you find statistical significance with a very small effect in those cases where you have, for instance, a very large sample size. On the other hand, it's also the case where you can have non-significance with a large effect because your sample size is very low. So sample size has an impact on power, just like the effect size. And so when you look at the significance level, it becomes, again, difficult to determine the magnitude of the effect that you're studying based on the p-value. So Cohen's d is one index of effect size. That's generally used in the context of carrying out t-tests. And so what I thought I would do in this particular video is just go over how to compute Cohen's d and really just trying to provide some fairly simple formulas and then demonstrate those computations with some illustrations using SPSS. So first off, when we look at the one sample t-test, this particular t-test is used when you are trying to compare a sample mean on your dependent measure against some null or test value. And so essentially, when you reject the null hypothesis, you're essentially stating that there is a difference between your null sample mean value and the null or test value. So let's take a quick look at the Cohen's d computation. So right here, this is it, and you can see in the numerator it's just simply computed as the sample mean minus your test value, whatever that happens to be. The denominator is the standard deviation for y, and that's essentially your dependent variable. So essentially, this value right here, the sample mean and the sample standard deviation, are computed directly from your sample data. And what we're doing, again, is testing a difference between your sample mean and that test value. Okay, then we can also carry out an independent samples t-test. And in this case, we're comparing two independent groups on a dependent variable. So we're fundamentally testing the difference in means between two independent samples. And the formula doesn't have that I'm providing right here is not really conceptually enlightening, but it is fairly simple to compute the Cohen's d value based off of an independent samples t-test. So essentially it's just computed by taking the t value from your output and multiplying it by the square root of your sample size for group 1 plus sample size for group 2 divided by the product of those sample sizes. So the numerator portion right here is essentially going to be your total sample size across the two groups, and then your denominator is essentially the sample size for group 1 multiplied by the sample size for group 2. So it's a fairly quick computation. The last demonstration involves the paired samples t-test, and with this particular test you're comparing the difference between your sample means and then you're taking a ratio of that difference to the standard deviation of difference scores. And I'll kind of show you a little bit more about that when we open up SPSS. Now, Cohen suggested some rules of thumb, primarily for the behavioral sciences, when it comes to making judgments about how large of an effect you're working with. So it's important to note that when you are, when you're computing Cohen's d and interpreting it, it makes a lot of sense to focus on interpreting your d value relative to the d values that are found in your previous literature on the same topic. But barring that, if there's not really much of a track record or anything of that nature, then he suggested some general rules of thumb for judging small, medium, and large effects. So a d value, an absolute value of d equal to 0.20 would suggest a small effect. A d value around 0.50 would suggest a medium effect. A d value around 0.80 would be an indicator of a large effect. And again, these are primarily for the social and behavioral sciences. The conventions in other fields of studies might have your d values higher, for instance, perhaps in physical sciences or something of that nature. So let's open up SPSS and run our analyses, and then we'll use a little Excel calculator that I've created in order to carry out the computations. So let's start with the one sample t-test demonstration. All right, and so we'll use the variable achieve, and for this variable we're not going to be looking at group differences. We're just going to look to see, let's say we have 16 students and we want to compare the mean on the achieve variable to a test value of 15. So to do this, we're just going to go to Analyze, Compare Means, One Sample T-Test, and we'll move achieve over to the test variables box, and for our test value we'll type in 15. Next we'll hit OK, and there you go, there's our output. And so looking at our output, we have a sample mean of 10.3750, and we also have a standard deviation. There's our standard deviation of 2.96367. So we're going to be using these two pieces of information in computing our sample mean using the formula that I laid out before, because what we need is the sample mean and we need the sample standard deviation, and we already know what the test value is, which was 15. So I am actually going to open this up and then go to sample mean, Cohen's d for one sample t-test. The sample mean is 10.375. The null value is going to be 15. And then the sample standard deviation is going to be 2.964. Hit enter, and so now you see that we get a negative Cohen's d value, but we're judging effect size, so it's really the absolute value that matters more than the direction. So in this case right here, using those Cohen standards, we would make the decision that the effect could be considered large. Okay, so that's essentially the calculation of Cohen's d. If you look in the little text box right here, you can see the computation. It was just simply cell H7 minus H8. Well, this is H7 minus H8 right here. Divide that difference by the standard deviation, which is this right here. Okay, so that's the one sample t-test. Now let's look at the independent samples t-test. So in this case, we're going to reuse the achieve variable, but now we have a group variable. And so just showing you what this is, imagine that our 16 individuals, they're students, and they were randomly assigned to either a treatment group or a control group, and we wanted to study whether there was an effect of treatment on the achieve variable or achievement scores. So in this case, we would carry out the independent samples t-test. So you can see that group is laid out in terms of group 1 and group 2 down here. So I'm going to go to compare means, independent samples t-test, move group down to the grouping variable box, click on define groups 1 and 2, move achieve over to the test variables box and click on OK. And so now looking at our output, we see that we have a sample mean of 11.375 and 9.375. Okay, so those are the means. The sample sizes are 8 per group, and then we have our t-value down here, which is 1.391. And going back to our formula and looking at it, you can see that we have the information we need. We needed a t-value and then the sample sizes for each of the two groups. So we're going to go into Excel, and essentially we're going to type for the independent samples t-test the observed value of 1.391, which is our t-value, sample size for group 1, sample size for group 2, and then you can see that our Cohen's d value is equal to 0.6955. So in this particular case, kind of going back to our rules of thumb, you can see that really the effect size is falling between kind of the medium and large effect designations. So I would pretty much refer to this effect as medium. So that's the independent samples t-test. The last demonstration involves the paired samples t-test. And so a paired samples t-test just involves comparing, taking observations that are paired. So essentially we have a measurement, in this case, two measurement occasions. There's a pre-test and a post-test. And the same individuals, each row could represent an individual. And let's say we were studying changes in math knowledge over the course of a semester. And let's say we gave these 16 individuals a pre-test and a post-test in terms of their math knowledge, and we wanted to see if there was a significant change over time in math knowledge. So the same individuals responded to the measure at two different time points. So that creates a correlation between the observations, and that's why we're carrying out a paired samples t-test. So let's run our analysis and then compute Cohen's d. So we're going to go to compare means, go down to paired samples t-test. We're going to move pre-test and post-test over to this box, click on OK. And now looking at it, you can see that we have our sample means of 4.0625, 4.625. And then down here, you'll notice the mean that's computed. This is just essentially the average of different scores, or essentially computed as the mean for group 1 minus the mean for group 2. So the mean difference is negative 0.56250. And again, that's representing essentially the difference in means. The standard deviation is a standard deviation of different scores. And so what I mean by that is that if we go back in here, we can compute different scores the following way. We can say the difference between the pre-test and post-test scores is equal to pre minus post. So essentially then each individual in the data set within this column right here would have a different score representing the change from pre to post test. And then the mean that you saw in the table down below is essentially the mean of those different scores, or by the same token, it's the difference in the actual means themselves. The standard deviation is the standard deviation of those different scores. So essentially, if we take the difference and then divide by the standard deviation of those differences, that will get us a Cohen's d value. So kind of going back here, this is essentially, this is the paired samples t-test Cohen's d version, or Cohen's d for the paired samples t-test. So we're taking the difference and dividing by the standard deviation of the difference. So in my little calculator right here, I just set it up to say difference in means is equal to negative 0.5625. Standard deviation is 1.8246. And there's our Cohen's d. And you can see that the absolute value is 0.30829. If we go back and we look at the rules of thumb, you can see that it's falling pretty much between small and medium, but I would pretty much consider it still a fairly small effect. So that pretty much concludes this demonstration.